Why is hydrogen bonding so important? If we examine the boiling points of the group 6 hydrides, we can see that the value for water is anomalous. We would actually expect water to be a gas at standard temperature and pressure. So why isn't it? To understand this, we need to state the 3 types of intermolecular forces, explain the relative strength of the different types of intermolecular forces, and explain how hydrogen bonding causes water to have a higher boiling point than expected. The atoms in molecules and giant structures are held together by strong bonds. But there are much weaker intermolecular forces that act between atoms or molecules, causing them to be attracted to each other. There are 3 types of intermolecular forces. Let's look at each type in turn. An atom, such as helium, is neutral overall. But at any moment in time, the electrons could be anywhere, so the distribution of charge changes at every instant. At any instant, the atom almost certainly has a small instantaneous dipole. This instantaneous dipole affects the electron distribution in neighbouring helium atoms, causing an induced dipole in those atoms. For that instant, the neighbouring atoms are attracted to the first helium atom by instantaneous dipole-induced dipole interactions. A moment later, the electron distribution changes and new dipoles are induced in the surrounding atoms. Instantaneous dipole-induced dipole interactions are stronger in atoms or molecules with more electrons. But what if the molecule has a permanent dipole? Chlorine is more electronegative than hydrogen, so the hydrogen chloride bond is polar. Hydrogen chloride molecules have a permanent dipole, so permanent dipole-dipole interactions act between them. These interactions are in addition to instantaneous dipole-induced dipole interactions and are stronger. Hydrogen bonds can only form in molecules where a hydrogen atom is bonded to a very electronegative atom with a lone pair of electrons. Only nitrogen, oxygen, and fluorine are electronegative enough to be involved in hydrogen bonding. Let's have a closer look at water. Oxygen is a very electronegative atom, so the bonds in water are very polar. We would already expect an interaction between the dipoles of different water molecules, but the oxygen atom in a water molecule also has 2 lone pairs of electrons. A lone pair of electrons on the oxygen atom is strongly attracted to an electron-deficient hydrogen atom in another water molecule, forming a hydrogen bond. This is much stronger than a permanent dipole-dipole interaction, though still about 10 times weaker than a covalent bond. So, how does hydrogen bonding explain the higher than expected boiling point of water? In all of the other group 6 hydrides, there are permanent dipole-dipole interactions between the polar molecules, in addition to instantaneous dipole-induced dipole interactions. But in water, oxygen is so electronegative, it is the smallest atom in the group with little electron shielding, that hydrogen bonding occurs. These strong intermolecular forces mean that more energy is required to separate the molecules, so the boiling point is higher. There are intermolecular forces between all atoms and molecules, but hydrogen bonding is the strongest. Hydrogen bonding only occurs between certain molecules such as water. It explains why water is a liquid at standard temperature and pressure, and is responsible for holding together the DNA double helix. Hydrogen bonding is vital for life. And we use hydrogen bonding to our advantage all the time. When we iron clothes, the heat of the iron breaks the hydrogen bonds that hold the clothes in a crumpled position. The pressure of the iron then flattens the clothes, and then the hydrogen bonds reform, holding the fabric flat.